my channel, and today I'm going to be talking about the history of physics. Physics, as we all know, has developed over the past few centuries and has expanded vastly in diversity and detail. In this course on the history of physics, I'm going to be talking about the 8 main branches of physics. The first branch, which we're going to be talking about today, is classical mechanics. The second branch is electromagnetism. The third branch is special relativity. The fourth branch is general relativity. The fifth branch is quantum physics. The sixth is astrophysics and cosmology. The seventh is essentially just string theory. The eighth is loop quantum gravity. So we're going to be covering these in a different video. So we're going to be talking about classical mechanics in this video. So what is classical mechanics? Classical mechanics essentially analyzes the motion of macroscopic objects or regular sized objects. So we're trying to find and analyze the motion of these objects. For example, if we take a ball, we're trying to find essentially where the ball will end up. Or if we throw a ball vertically up into the air, we want to know what's the highest point the ball will reach, and we can use calculus and classical mechanics for that. So classical mechanics is very useful. So who are the founders of classical mechanics? Well, Isaac Newton and Galileo Galilei are regarded as the main founders of classical mechanics. Both of them were also astronomers because Galileo Galilei created another telescope, which was very important, and Isaac Newton created the reflector telescope, which is a little bit more advanced than the telescope Galileo Galilei created. Now, Isaac Newton and Galileo Galilei did more than just create telescopes. For example, Galileo Galilei proved Aristotle wrong, and Isaac Newton developed much of the classical physics we have today. For example, Isaac Newton developed the universal law of gravitation, and this is essentially just helped people track other planets around our solar system. For example, we could track the orbit of Venus or the orbit of Mars using the universal law of gravitation and essentially find out where it's going to be in the night sky on a particular day. We can use Isaac Newton's universal law of gravitation for that. So, the universal law of gravitation and many other things that Isaac Newton and Galileo Galilei invented are very, very important and crucial to the modern world today. So classical mechanics also has another reason of why it's important. Classical mechanics essentially is the foundation for all the other branches in physics. So for example, take this. If we didn't have classical mechanics, then we wouldn't have electromagnetism. If we didn't have electromagnetism, special relativity, general relativity, quantum physics wouldn't have been developed. And the rest of these branches are essentially just byproducts of these 5 essential main theories. So astrophysics, cosmology, loop quantum gravity, and string theory would not exist because if classical mechanics would have been not created. So if classical mechanics were not to be created, then electromagnetism were not to be created, and special relativity, general relativity, quantum physics, astrophysics, cosmology, string theory, and loop quantum gravity all would not exist. So that's why classical mechanics is very important. Now you may be wondering, Isaac Newton was born on January 4th, 1643, and Galileo Galilei was born on February 15th, 1564. Now if they were born on these years, then what happened before Galileo Galilei and Isaac Newton existed? So what I mean, was there any pre-existing theory before classical mechanics? Well, before physics came up, people just used astronomy and mathematics. So most astronomers were mathematicians, and most mathematicians were astronomers. Astronomers even invented trigonometries to study the night sky. So astronomy is essentially just trying to track the motion of other planets and try to essentially find them and record them, which also is what the universal law of gravitation does. But we really don't want to understand why and how these objects move in the night sky. Astronomy is just trying to map and understand them. So when physics came into play by Isaac Newton and Galileo Galilei, we got a better understanding of the universe itself and our planet Earth, because we really didn't want to understand before Isaac Newton and Galileo Galilei why do things behave the things they do. For example, we didn't ponder the question of what are we made of really that much. We did when the Greeks came, but after that we slowly started moving into astronomy and we really didn't focus on that question. Physics came along and answered these questions like particle physics, quantum mechanics, general relativity, and so on and so forth. A simple question that Isaac Newton asked was, what makes the apple fall, and is it the same as why the moon orbits the Earth? And that revolutionized physics itself, because Isaac Newton, with Galileo Galilei, independently created classical mechanics. So Galileo Galilei created one part of classical mechanics, and Isaac Newton created another. So one of Galileo Galilei's important contributions is that he proved Aristotle wrong. For example, let's use our common sense and try to understand a physical situation over here. So, if we erase this, okay, so we can essentially see that if we have two objects, one with mass 1, m1, and one with m2, and now we're going to time how much time it takes for these objects to fall. So for example, we want to see which object falls faster. Now normally, we can state that mass 2 is greater than mass 1. Then, the thing we would normally predict is that mass 2 would fall, or m2, which is the object's name, would fall faster. And this is true, because normally on Earth, both of these objects, if we take a feather and we take a brick, the brick is going to fall faster. Now, what Galileo Galilei proved, and essentially went into more detail, is that if we took a vacuum, where a vacuum means there's no particles, nothing, except mass 1, mass 2, and we take mass 1 and mass 2 and we drop these objects at the same time, what would happen to these objects? Well, they would fall at the same rate and they would hit the ground at the same time because they're in a vacuum. So that means that when we essentially have Earth over here, Earth has multiple more forces like air resistance and so on and so forth. These factors affect these objects, and it's why one object falls faster than the other object. So if we take a vacuum, the shape, size, weight, they don't really matter. Both of the objects fall at the same time. So that's what Galileo Galilei revolutionized. Okay, now that we've talked about what Galileo Galilei did, let's talk about pretty much what Isaac Newton did. So as I mentioned, Isaac Newton essentially discovered the universal law of gravitation, and he also discovered the 3 laws of motion, which are taught worldwide. So the first law of motion is inertia. Which just means that if we have an object, and that object is in motion, then the object can't slow down or become stationary unless another force acts on it. For example, friction. Then, it also states that if we have an object that is stationary and it starts to move, that means a force must act upon it so it can move. The second law is an equation. Force is equal to mass times acceleration. The third law is essentially just for every action, there is an equal and opposite reaction. Now, so we have inertia, F is equal to ma, and for every action there's an equal and opposite reaction. Now, F is equal to ma is heavily used worldwide. For example, we can use it along with the universal law of gravitation to track planets across the night sky. And we use this also for many other things, for buildings and for objects rolling down, for cars. We can use it for tons of things. So F is equal to ma essentially is used a lot. These other 2 laws are essentially just laws because we can observe them happening. So these are the Newton's laws of motion. We also have Newton's law of universal gravitation, which is just F is equal to G times m1, m2 over r squared. This is also called the inverse square law. So if you're taking algebra, you probably know that there's a direct and inverse. So direct just pretty much means we have y is equal to kx. So we have something multiplied to it. Whereas inverse just means y is equal to k over x. Now, as you can see over here, the x is going to be r, or r squared. So that means we have an inverse. So what this means is if we analyze this equation mathematically, we can state that, for example, if the distance between an object, or between 2 objects, are greater, which means that r squared is going to become bigger. For example, if the distance between an object is 5, we're going to have 25. If the distance between, for example, it's 36, and we have 36 squared. So it means that if the distance is essentially just getting bigger and bigger and bigger, essentially the force gets smaller and smaller and smaller because we're dividing by a greater value. So we can deduce that, and that also is common sense along with this equation. So we can deduce that the inverse square law is right. Okay. But Isaac Newton just didn't develop these things. He also experimented with other mathematics, for example, the binomial expansion. And he also created a branch of mathematics which also revolutionized mathematics itself, which is called calculus. Now, Isaac Newton mainly developed calculus to help with his research on physics and classical mechanics. So, for example, if we erase this, so for example, we can state that calculus was developed for physics. So this is a statement that we can say. Now you also may be wondering, if calculus is developed for physics, is it used in physics? Well, all the other branches that I talked about involve calculus, and classical mechanics does too. So if you take any branch of essential physics, you will probably see that there's at least one equation or one formula involving calculus, because calculus is really important. Now, it's important to realize that Isaac Newton just didn't develop calculus. Gottfried Leibniz in Germany also developed calculus too, but they didn't work together, because Isaac Newton worked a lot in isolation, and he worked a lot singularly, so Gottfried Leibniz also developed it. So they both developed it independently at nearly the same time, which is pretty interesting. So calculus was also developed for physics. Isaac Newton called it fluxions. So Isaac Newton made a lot of contributions to classical mechanics. So for example, we can calculate using kinematics the motion in an object, the velocity and time an object is going. If we just know one or two of the initial conditions, we can essentially derive the final velocity or the initial velocity, or so on and so forth. So kinematics shows that. Kinematics is essentially when we're trying to find conditions and motions of the object without considering the forces. Dynamics considers all the external forces too. Dynamics. So these are two of the main important branches inside of the branch classical mechanics, kinematics and dynamics. So classical mechanics is essentially revolutionized physics itself. So let's summarize. The main people who essentially discovered calculus was Galileo Galilei and Isaac Newton. Of course, there were many others that also developed to it, but Isaac Newton and Galileo Galilei are regarded as the founding fathers of classical mechanics. Without classical mechanics, all the other fields wouldn't exist, because classical mechanics is the foundation for everything. Classical mechanics is essentially just trying to analyze the motion of macroscopic objects in the regular size. So that's essentially what classical mechanics is. After we talked about classical mechanics, we talked about how Galileo Galilei disproved or proved that he was right when considering that two objects fall at the same rate and same speed and reach the ground at the same time in a vacuum. In Earth, since we have multiple factors and forces, that's why one object seems to fall faster than the other object. Isaac Newton also developed many other fields, like optics and classical mechanics and the universal law of gravitation, and we covered what the universal law of gravitation is. The universal law of gravitation is also used in NASA today because it's very, very crucial. Even if Einstein developed a better theory of gravity, Isaac Newton's equations still hold today. Now that we've talked about it and summarized, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.